All right, so let me first thank Alvaro for inserting a time slot into the schedule for me to speak. So I guess, and then in turn, I should apologize for a couple things. One is keeping you from your lunch. I'll stay on time, I promise. Two is that I didn't have time to write slides because I've been teaching until Friday. And third is that I mentioned the word formalizable. So there's some hint of formalization. I've been teaching a class about lean this term, but I'm not going to do any formalization in this talk. But the motivation is to try to organize the math in a way that will make it easier to formalize later. And I hope that also makes the talk easier to formalize. The talk easier to process. So in that spirit, let me start with, okay, so some context. So throughout this talk, to be a local in the usual sense of algebraic number theory. So it could be one of the following things. It could be, right? So a local field is what you get when you take a global field, which is a number field or a function field or a curve or a finite field, and you complete with respect to some absolute value. So the kind of classical examples are R and C, or you also get finite functions of the p-adic numbers QP, or you can also get a finite extension in positive characteristic. You might get a finite extension of the field of rational function, the field of formal power series over some finite field. Might as well be FP, because everything else will be a finite extension of that. So if you have one of these things, so number theorists think a lot about things like the local Langlands correspondence, which I won't say anything in detail about. This is just the context. So there's a lot of interest in kind of formulating the local correspondence in particularly convenient ways. And in particular of kind of using geometric tools. So this local Langlands correspondence can be described sort of uniformly in terms of some sort of curve in quotes associated to E. So I'll say what I mean by curve in quotes in a moment, but let me give you two examples which are kind of curves in a more familiar sense. So if E is C, then the thing you're supposed to use is just the projective line. So let's call this curve X. X is just P1, which in order to compare with what I'm going to do later, I'm going to spell out explicitly as, you take proj of a graded ring, which is, well, you take a polynomial ring in two variables over C. And so this is a pretty familiar geometric object, P1. And it is indeed, by pretty much any definition, it's a curve over the complex numbers. Sort of the first curve that anyone ever knew about. So when E is R, you're supposed to do something slightly more exotic. So you take something that is commonly called the twistor line. This terminology goes back to Carlos Simpson. And the thing you're supposed to take is, I'll write it as a proj first. So you're supposed to take a graded ring where you have three variables and one relation. And so if you stare at this for a moment, what am I doing? I'm taking this is the homogeneous coordinate ring for a conic over R that has no rational points. So, it's defined over the reals, but every point has residue field C. So then So the kind of discovery that Fargues-Fontain made in the mid-2000s is that there is a thing that kind of goes here. and has certain kind of formal similarities with these guys. So now let me unpack what I mean by a curve. So it still has the kind of abstract scheme theoretic properties of a curve. So it's a regular one-dimensional Noetherian scheme. So in particular, another way to say this is that it's built out of, it's covered by pieces of the form spec R, where R is a Dedekind domain, the sort of ring we're used to when we do algebraic number theory. So, right, Dedekind, like the ring of integers in a number field has these properties that guarantee unique factorization into prime ideals. So that's the kind of ring that we use to build these things. And in fact, a curve, right, if we think about curves in the traditional sense, okay, right, this is not spec of a ring, but as soon as I take out one point, it is spec of a ring. So in fact, the complement of each closed point is spec R. So as soon as you take out one point, you're looking at the space associated to some ring. That ring is a Dedekind domain, but in fact, it's actually even better. It's actually a principal ideal domain in this Fargues-Fontain construction. That's true classically in these two examples. In this example, right, the complement of, say, the point at infinity would be the spec of C bracket one variable. This is regular. Sorry, I accidentally drew a double bracket here. That's a single bracket. Right? A polynomial ring in one variable is a principal ideal domain, not just a Dedekind domain. And it's a slightly more challenging exercise, but not so difficult if you want some sort of an algebra exercise to think about during the talk. If you take a point out of this thing, the result is also a principal ideal domain. So those are some properties that the thing that Fargues-Fontain write down have in common with these examples. Some more features that it has in common. Every closed point has algebraically closed residue field. Okay, so that's clear here by the Nullstellensatz. The residue field, it's Nullstellensatz for P1. It's just the fact that, it's the fundamental theorem of algebra, if you want. So here is a little more interesting, right? As I mentioned, this conic has no real points. So every point has residue field C, but the interesting thing is that the copies of C that you get are somehow different. In particular, if I give you two copies of C, they're not canonically isomorphic because there's an ambiguity about, do you match up this square root of -1 with this square root of -1 or with the other square root of -1? And so the copies of C that you get by reducing modulo various points don't come with a specified indication of how you match up I and -I. So you should really think of them as all sort of different copies of C that share a common R, but they don't know how to sort of automatically compare to each other. And that's somehow even more extreme. In this case, you get residue fields that are, in some abstract sense, they're all isomorphic. They all look like a completed algebraic closure of, your local field, but they're not related in natural ways. So it's more like this example than like this example. So that's another feature. Another feature is that so there's a degree map. So if you so the degree map. So if you take divisors on this, so this is a one-dimensional thing. So when I say divisors, I just mean like formal linear combinations of closed points. So this thing has the property first of all, it has the kind of property you would expect that principal divisors have degree 0. But the more interesting part is that the kernel has kernel exactly the principal divisors. So exactly the principal divisors. So that's a property that, P1 of a curve has, but a typical curve over the complex numbers does not have, right? If you take a higher genus curve over the complex numbers, then there are lots of degree 0 divisors that are not principal, and that's related to the fact that the Jacobian, as came up in the previous talk, is something interesting. So in this case, we don't have an interesting Picard group. The Picard group is just Z, so every line bundle is just indexed by its degree. And one other thing that it turns out is true in these two examples is that if I take h1 of x with coefficient in the structure sheaf, that's 0. Again, this is not something that's typically true for a higher genus curve, right? This would normally be like the genus. It's true in this example. It's also true in this example. But there's a distinction between these two examples that we see here. If you take O minus 1, then in the classical P1 situation, this would be 0. But already in this situation, this thing is not 0. It'll be one-dimensional in that case. And in this case, it'll be actually extremely large. So somehow this is it's like P1 when it comes to this, but it's more like this funny example when it comes to O minus 1. So those are, so this is in subsets the list of properties that this thing has, and it pretty well mirrors the properties that are shared by these two examples, except for the fact that these examples are finite type schemes over this. And so, however, in the Fargues-Fontain case, there is this thing is defined over, I should say it's over E. So there is a morphism of schemes from X to spec E, but it's not finite type. This X cannot be described in terms of polynomials over E with finite number of variables. It's some very infinite thing by comparison. But somehow, when you don't think about E, when you think about it internally, it does seem like one-dimensional in some kind of abstract sense. So, and so so this is in some sense all I want to say about the actual Fargues-Fontain theorem. I don't want to try to give you the definition of it. It involves some kind of an intricate p-adic analysis. You have to, you have to make something in characteristic P. You take vit vectors. There's some mucking around. It wouldn't be very enlightening if you haven't seen it before. But again, in the context of thinking about formalization of mathematics, it's important to do as much as you can with, without minimizing the extent to which you have to unpack definitions of things. And so the general premise of this talk is kind of inspired by my formalization class, which is how much can we say without unfolding the definitions further? And part of the motivation for that is I would like to make statements that are actually uniform between these two cases. So there is the theory of vector bundles on this thing has a nice classification result that is parallel to the classification of vector bundles on P1 is a famous theorem of Grothendieck that I'll recall the statement of. And there's so when Simpson introduced this construction, he was able to derive an analog. So I want to formulate the theorem that classifies vector bundles in a way that sort of operates uniformly in these cases. And then the question becomes, how much of the proof can I make both uniform and also kind of independent of finer properties of the construction other than what I've written on the board? So other than sort of things I can say in the language of schemes without knowing any non-Archimedean analysis. Okay, so now we need to start talking about vector bundles. So I already mentioned line bundles, right? So this statement about the degree map having kernel exactly the principal can be interpreted as saying that every line bundle is determined by its degree. So a line bundle you can think of it as you're picking, you pick some divisor and then you're looking at functions, rational functions whose poles are bounded below and whose zeros are bounded below by this divisor. But this theorem is going to be about higher dimensional vector bundles, and so those maybe you want to think of more going back to the definition, right? This scheme, whatever it is, it has pieces which look like speck of rings. So what you want, a vector bundle is going to be like since I'm talking about PIDs, I can say a finite free module over this ring, for each, right? So if I think of covering this scheme with a couple of different specs, then like right here I have spec R1, here I have spec R2, and the overlap is going to be some overlap is spec R3, right? Then a vector bundle will consist of a vector bundle will consist of data like a module, so a finite free module, mi over ri for I equals 1, 2, 3. But it should have the property plus you want isomorphisms, right? M1 is a module over R1. R1 will map to R3. And so that should be the same thing as M3, and that should also, and likewise, like this. You don't really need to put R3 in here. I could just put in the M1 and M2 and give this isomorphism. But it's nice to say it this way. So, right, so it's like it's the analog of a module, of a finite free module in this situation where you don't just have spec of a ring, so you don't just have one ring to worry about. There are different rings that can occur, and for each one you have a module, and they have to sort of agree when you shrink down your affine subspace so that you pass from one ring to another. And so in particular, the module theory over some general scheme is potentially quite complicated, even if the pieces are nice. I mean, modules over a PID are very easy to understand. So anything you can say that's sort of local about one of these things, like finite torsion free implying finite free. Well, free is a complicated condition. You don't expect to be able to, I mean, the vector bundles in this case are not all going to be just trivial, even after accounting for the fact that they have a degree invariant, which is something non-trivial. But in some sense, they split up into relatively nice pieces. So let me state the classification theorem that this talk is about. And I'll state it in terms of some terms that I will still need to define. But so the theorem is going to say something like every vector bundle is a direct sum of pieces that look like so. So another way to say that is I'm going to classify the vector bundles that are indecomposable, that cannot be split as a direct sum. So indecomposable means, well, not the zero bundle, just like, like 1 is not a prime number, so the zero bundle is not indecomposable, and not a non-trivial direct sum. So which are the what are the basic building blocks in this category? So a vector bundle is going to be indecomposable if and only if it is what's called stable, which I will tell you what the definition is in a moment. Actually, let me try to unpack the definition now. So if you have a vector bundle of some rank, so if you have a vector bundle of rank 1, then there's a numerical invariant attached to it. Now this extends to a higher rank vector bundle. If I have some vector bundle V, well, what you do to make degree of V is you just say, right? Just like with modules, you could do things like symmetric powers and exterior powers. So if I take the exterior power of this thing to the highest possible degree before I get 0, then I get something of dimension 1. And so that has a degree. And so you define the degree of V to be the degree of this thing. So that's somehow not as you're losing information. You don't expect to be able to say all the information about a vector bundle by just this, because you've sort of thrown away a lot of information by going from this n-dimensional thing to this one-dimensional thing. But this degree is still an important piece of data. And another thing you can define out of this degree, and this has its origins in studying moduli, actually constructing moduli spaces of curves and this kind of thing. This is an important geometric concept, is the slope, which is just the sort of average degree. So it's degree divided by rank. For some reason, it's often in mu. I don't know what mu stands for in this context, but so the slope is mu of v is the degree over the rank. This only makes sense if the rank is not. The degree of the zero bundle is, I guess, automatic, is just, well, yeah, I should say the degree of the zero bundle is 0. And all right, that convention has the property that well, you could say something about degrees in sums and tensor products. So a degree, so if you have an extension, so this is right. This is sort of a module theoretic analog of the property that if I have a block upper triangular matrix, that its determinant is the product of the top left determinant and the bottom right determinant. The module theoretic analog of that is the fact that degree of V is degree of V1 plus degree of V2. And there's also a statement about what the degree of a tensor product is, which I won't try to write down. But so this is a kind of basic numerical invariant that, and the theorem is going to give content to the form. These indecomposable vector bundles are determined by, well, okay, there's this, okay, I'm going to still skip this word stable, but let me say that there is at most one isomorphism class, so this is kind of one point, there's at most one isomorphism class of vector bundles, of indecomposable bundles of a given slope. So this numerical piece of information, which is quite crude, actually is a complete isomorphism class invariant for these indecomposable things. So that's actually very surprising. That is not at all true in usual situations if you take like some genus G curve where G is non-zero. And so this is a very unusual thing that's going on. And I guess I'll also mention, so slope doesn't necessarily, like the fraction here doesn't necessarily occur in lowest terms, right? Just because I have something of slope a half doesn't mean it's like degree 1 over rank 2. It could be conceivably degree 2 over rank 4. And so it's an extra piece of information to say that if you get something of slope 1/2, then it occurs, quote, in lowest terms, which I think hopefully is unambiguous, meaning that whenever you have an indecomposable thing, the degree and the rank are coprime. So these are really as small as they can be. And finally, I can tell you which slopes occur. The slopes that occur, and I'm going to say it in a way that is a little bit cryptic, but is actually meaningful for number theoretic purposes. So, right, the slopes are rational numbers, because I'm dividing two integers. So, and they form a subgroup of Q with the property that, well, it's going to contain Z, because every line bundle is automatically indecomposable. So integer slopes definitely occur. So, but in general, there might be fractional slopes. And the ones that occur have the property that S mod Z is isomorphic to the Brouwer group of E. Now, what does that actually mean? What that means is that in other words, so S equals Z if E equals C. The Brouwer group of an algebraically closed field is trivial. If E is R, then the Brouwer group is Z mod 2, so this group is integers and half integers. Right? The Brouwer group of the real numbers has exactly one non-zero class corresponding to the Hamilton quaternions as a division algebra. And otherwise, when you take another local field, the Brouwer group is Q mod Z. That's a basic piece of information from local class field theory. And that matches up to this. So I write it this way not just because it's not just shorthand there is actually a close relationship with the Brouwer group, which is that the endomorphisms, right, the maps of one of these indecomposable guys to itself will actually always be a division algebra. So this and it won't depend on right, if you sort of multiply by if you tensor one of these bundles by O of n, you won't change that division algebra. So in fact, this bijection is not just numerological. It actually is sort of structural and plays an important role in the local Langlands. So this was observed by Fargues that this sort of structural relationship is not just an accident. Okay. So that's the theorem, except I should tell you what stable means. So let me say what stable means, and then yeah. So we're gonna let me leave this here so I can still point to it. And let me finish stating the theorem by telling what stable means, and then I can say a few things about this and the proof, the sort of formalizable proof that I'm going after. So stable. So V is stable if for every non-zero proper subbundle W of V, we have mu of W is strictly less than mu of V. So so one thing I should point out before I keep going with this is that, right, there are these, so if I take O of 1, it has copies of O in it, which has copies of O of minus 1 in it, and so on. So there exist inclusions like this. So, you know, degree goes up when a sort of bundle gets bigger in some sense, at least when you preserve the rank. So in particular, line bundles have this property because every non-zero proper subbundle of O has to be down here and not over here. But this is meaningful for higher rank bundles too, and this turns out to be a good condition that picks out these indecomposable guys. Yeah, so that was the missing piece here. So yeah, as a reminder, in the case of P1C, this is an old theorem of Grothendieck. Right? In this case, it's saying that the indecomposable bundles are the line bundles. And so this is a statement, every vector bundle on P1 splits into line bundles. So that was shown by Grothendieck. So in the twistor case, so maybe I'll write for E equals C, this is the theorem of Grothendieck. E equals R, this was deduced from the E equals C case by Simpson. And then for other E, this is, well, in the form that I've stated, this is due to Fargues-Fontain. But this work takes input from various other places, like a previous paper of Colmez and Fontaine, and a paper by me and other people. So, yeah, and the thinking was definitely that this is meant to look like the Grothendieck classification. But the thing that maybe was not so clear at the time, and we're sort of starting to look at now, is that actually quite a lot of the proof can be done uniformly in the different cases. So let me sort of state the goal of the project that I'm working on is sort of on one hand to give a uniform, as much as possible, approach to these results, and I should say with an eye towards formalization. So as I said, I've been teaching a course on lean this quarter, so I now kind of write, these lean proofs for various things. Writing a proof at lean typically depends on having the prerequisites being available. So for example, if you want to write an argument about schemes, you don't want to be the one to have to define schemes. You want somebody else to have done that in lean. and that exists. So schemes exist in Lean. Not so much vector bundles, but since I can think of these things in terms of modules, one can try to do this by mostly kind of fiddling around with modules over PIDs. So, modulo some messiness in how you actually implement things. The technology to do this is mostly there as long as the arguments are about schemes. And, well, the arguments are not completely about schemes in this case, at least not so far. Even setting aside the input, which is something we would do separately, of proving that the construction of Fargues-Fontain does this. So that's sort of one piece that is actually something that I'm hoping to work on, but maybe not right away, is actually doing the underlying p-adic analysis to the extent of being able to check these properties. But then the real question is, how much of the proof can you run just using these properties without having to know anything more about p-adic analysis? And when I proposed to give this talk, I was sort of optimistic that I would be able to do all of it. Now well, it's still in progress. But I can make a key point which illustrates how you want to think about this proof differently than the way Fargues-Fontain set it up. So Fargues-Fontain kind of knew you could explicitly construct the candidates for these stable bundles. So I'm not going to go into it because I don't want to unpack definitions, but it's a kind of pretty direct construction that gives you the candidates for these stable bundles. And then the theorem becomes trying to show that every indecomposable bundle is one of these things. So here, I don't want to start with that information in advance. I want to kind of discover that later. And so but one special case that should be true is that any stable bundle of degree 0 is, well, there's only one. There's the structure sheaf. And so the idea is to first try to prove this. So at the moment, you need some non-trivial input from p-adic analysis to do this. But then this allows you to do things like prove that any tensor product of stable bundles is, well, not necessarily stable, but it's semi-stable, or better yet, actually, I can even say it's a direct sum of stables of a single degree, of a single slope. So normally, instead of stable bundles, you work with semi-stable bundles where you allow a non-strict equality here. So then you might want to phrase this as any tensor product of semi-stable. This is even stronger. This is saying that a semi-stable thing will also split up as a direct sum and not some weird extension. And then you sort of keep going. Then you kind of do the rest. But so maybe I think I don't want to actually even take the allotted 45 minutes. Let me just try to wrap up by saying, this reduces somewhat further. So maybe I'll clear this. So I'll mention the idea of the proof here. So the idea of the proof here is consider filtrations of V where sort of maximal, maybe you could call these complete flags. We call complete flags. In V, so V is some vector bundle of some rank. So you have some sequence of inclusions. So each of these quotients has rank 1, and so it has a degree, and it's actually equal to O of that degree. And then you analyze the possible sequences. And when Mn, you need some input about these things, like you need to say that like the partial sums are bounded above, and very crucially, you need the key lemma is something like, if you see a sequence like, if you have some sequence that looks like this, -1, 0, 0, 0, 1, you can replace this flag with a different flag that replaces all of these with zeros. So you kind of you start with one of these flags. First you prove the existence of one of these flags. Then you prove some kind of replacement lemma that if you see certain structure, then you can modify it. Then you get some kind of combinatorial constraint on the set of sequences that you can turn into a proof that there has to be and eventually you deduce that the sequence 0.0 occurs. And this part actually I have semi-formalized in the sense that I sort of wrote down the combinatorial statements that come out about existence with certain properties, and that is something that it turns out is not too bad to formalize. So that's kind of the lesson here, is that even in some situation when you have kind of mathematical concepts that are not maybe ripe for formalization, you often can isolate certain pieces of arguments that are sufficiently elementary that those can be formalized, and then you can kind of build in the direction of formalizing a whole proof out of these concrete pieces. And there's also sometimes you even just want to know whether this concrete argument is okay. In this case, I didn't have any doubt about it, but you can imagine other situations where you have some very complicated combinatorial argument. You don't know if you trust yourself, so you formalize that, and then you feed that into some deeper piece of mathematics that maybe you didn't formalize. All right, I think I'll stop there. Thanks.